Thank you very much. Questions? Please.
In terms of translating the model that you have you plan to use in predictive medicine to commercial application, is a model something that someone can own and sell? I'm told that the intellectual property gets quite tricky because you can always add or subtract something from the model and have a new model that you then don't own. Can you comment on that?
Yeah, so the answer was easy about 20 years ago, and it says you cannot own mathematical constructs or theorems or proofs or anything mathematical. You cannot own it. And then people started saying, yeah, we're not selling the model, we are selling the algorithm and some machine that implements that algorithm. Now, that was a dirty trick. And now it's really a big gray zone. And I don't think anybody really understands how that works. Now, there are companies out there like Entelos in California that sell models to, for instance, Johnson & Johnson. And they really go through the literature and put everything they can find, put into those models. And they have one for pertussis, and they have a couple others, I forgot what they're about. And they're very complicated models, and they will never divulge what their exact specification of these models are. That's sort of their trade secret. But they do sell them to Johnson & Johnson. So I would imagine that something like that would be happening rather than, patent production or something.
Professor Barenholtz, please.
I think the only way is really trade secret. There is no other way, and go for specific things to do. Mm-hmm. And you can have a patent on a specific application, but you always have to keep. But that's not what I want to comment. I think we use a lot computational not biology, but computational approaches to more and more things. And there are a few problems with them. One, you need a lot of data. Otherwise, it's meaningless. So if you don't have a lot of data, you can use other type of approaches like decision trees and something like that, other ways, like we're using Weka a lot and things like that. But still, I remember when I started with this, I have a very simple problem I want to solve. And actually, think that I knew the solution. So I went to a theoretical computational biologist, and I said, I want you to figure out how many molecules of water are attached per polyethylene glycol of this size. Okay, very trivial thing. So I knew the number. We have it by two different methods. I came to the guy. I gave him the calculation. He came after first time, and it was no resemblance to the real life at all. So I said, no, sorry. He tried again. At the third time, he succeeded to do it. But once he succeeded, now we use his model, and it works every time. So I think he put enough information in it. He asked me a lot of questions. So the problem with these things that you have to find a way to build the model that it will be a robust model and not something that you will have so many false positive and negative in it that it has no meaning, like many of the models are. And that's what bothers me in this, that we become, in a way, dependent on this model. The relationship is very, very strange. The model people are dependent on the practical people, but then you have the opposite relationship. Now, say someone came to you, and even the FDA will say, there is a model, but your data doesn't agree with the model. So you have a problem, or the model have a problem? I think most of the cases, the model has a problem, because they don't have enough information to deal with it, not because it's wrong, but because they still not ready for it. So I think that's really a very, very crucial point that I'm looking for answer to you, being a layman in the modeling, but really using it quite a lot.
Okay, I could talk for about an hour and a half about this answer, which I will not do. Rest assured. So, two short answers. One, in comparison to biology and biochemistry, modeling is very, very young. If you look at the first models that had anything to do with biology, it's not really all that long ago. I still worked with, solving 3 differential equations on a mainframe computer at the University of Michigan, not at Podunk. I mean, this was a good, university, and it's not that long ago. So we are way behind. The expectations are sky high. We are trying to hit the moon with a slingshot, and we're not going to hit it anytime soon. Having said that, if you look at the analogy with physics and engineering, we are able to predict how to send a little machine slingshotting around Jupiter, ending up at Mars, dropping off a little other machine that's running around as predicted and send it photos back. That's where we will come in the long-term future. And if you say most models are wrong, yes, I agree, because we don't have enough information. But I think eventually we will not have a choice anymore. It's easy. If this group and a few physicians got together, you could take 10,000 biomarkers easily of any person in this room. Now, who can evaluate 10,000 biomarkers and you take them, let's say, every week? Who can evaluate that over time? It's not possible anymore. So the models need to become better, but we are still in the slingshot phase, and they will become better. That's our job security.
Well, if I just add my own experiences with this, when we were doing a lot of field work looking at hepatitis B virus and clinical studies and biological studies on the virus, and we wanted to get some kind of overall picture of the dynamics of epidemics and pathology and the consequences in the general population for a very widespread infection. And at that time, I was visiting the institute, the Santa Fe Institute, where they kind of specialized in chaos at the time. And I would show them all this stuff, and the first thing they'd say was, well, which variables can you get rid of? And my reaction was, wait a minute, I've just spent all this time collecting all the variables. I don't want to get rid of any of them. That was an impasse. But I think your prediction, starting off from, physics of being able to land a satellite on Titan after sort of 8 years sitting in Cassini is nothing short of remarkable. But biological systems aren't, as I needn't tell you or anybody else here, are not the same. But it's very encouraging, the continued approach.
Yeah, I think if you look at the number of people who actually have devoted a lot of effort to modeling in the past, which is a very, very small number in comparison to biochemists and molecular biologists, and you look at the rate of progress, it is encouraging.
Yes.
But it will take a long time before we're there.